Okay, hi. Hi everyone. Uh, Welcome back. Today I'm going to talk to you about a very famous experiment. It's called double-slit experiment, and it's a paradigmatic experiment that can be done in the lab, for example. At least um, it's not difficult, but it's not complicated to imagine this experiment. It's very simple. And it goes into two of the fundamentals of quantum mechanics that I touched upon in the introductory video that I already made. That is superposition and superpositions and collapse. Oops, this is uh, collapse of the wave function. So what are these two things? I will go briefly back to give you an idea or refresh what we already said. Suppose we have a total wave function of x and t for a certain observable, for example, the velocity. We are looking for the velocity of an object, a classic quantum particle, which is moving at some speed, and then we have a wave function for that. So we have its amplitude that can give the probability of the distribution. But we have two possible outcomes that are equally likely. For example, 1 x and t, and this will be v1 plus v2. And this is because the system is such that it prefers to stay in two states rather than in one. And the superposition happens in the quantum world, where the probability didn't happen yet, and these are still complex numbers. So those two are potentially happening together. But then there is the collapse of the wave function that tells you that in the real world, only one of those two will will happen, and you will either have one or V2 in after a measurement or after an interaction, whenever the collapse happens. So what is this collapse? We don't know why or how it happens. We know that it does happen when there is an interaction or a measurement. Measurement M, you measure your uh, wave function total with certain value 1, for example, of the velocity, and then you take the modulo square. And this is a probability. Sorry. This is a probability distribution, and it comes from the probability amplitude, which is a complex number. While this is a complex number, this is a real number, so we can count with this probability. It is what happens and this is happening in the quantum world, let's say, and this is classical. So what we see around, usually we don't see superposition, we only see things that already collapse. We don't perceive the collapse of the wave function, but we know that it happens because in experiment in the lab we can see interference, as we will see in this video, that tells us that these superposition do exist and do have an effect in real life. But we don't see them because, well, nobody knows why, but there are theories out there that talk about, for example, multiple universes, or there is maybe a hidden variable that says randomly when the wave function collapse, or other where the observer are not unique or not absolute. So there are relatives observer that determine somehow the collapse of the wave function because you just see a subset of your system, not the entirety of it. So anyway, well, whatever theory we have to explain the collapse, we know that it exists. And let's see what happens in double slit experiment then. So for example, first of all, what is a slit? A slit, suppose you take two pieces of metal, thick metal in this case, because we are using bullets to begin with, and you put them one next to each other. And you let the space between them D, which is a slit. Exactly. And then you take many objects of the same kind, particles, bullets, balls, whatever you want, with mass m, and then you shoot them with velocity v towards the aperture of the slit. Some of them will bounce back, but there will be few of them. We can neglect them. Most of them will bounce forward in the correct direction with some velocity. Some of them will take a different trajectory because we'll hit the walls, for example. It doesn't matter what's the exact physics of it, but we know that at some point we will collect these balls or bullets at the end of a screen or whatever you put at the end of this experiment you want, and you collect as many as you want, suppose 1,000, and then you will see that the vast majority will be bounced at the center of the slit and very few at the edges. And you can believe me that with the law of large number, this can be well approximated by a Gaussian distribution. Okay, very simple, single slit with purely classical objects. Now, what happens? We do an intermediate step, and this is a particle behavior. You see, particle behave because one at each time, and they go through the slit, nothing happens, they go in a straight line, and they have been collected once, one at each time on the screen, and this is particle behavior. So let's print it here, particle behavior. I hope it's written correctly. Now let's say the wave behavior. So still a classical experiment. We have a source of light here that is creating a wave. The wave touches the slit, which is smaller than the wavelength, for example, or even slightly bigger. And then it will expand as a wave and will touch a screen. And of course, the intensity of the wave will be, as you can see, bigger in the center and smaller at the edges. And then you can see that it will be something like this, maybe another Gaussian or some function very close to a Gaussian. But the intensity will be in one lump. All the intensity will be distributed along the screen at the same time, if you like. So this is a wave behavior. It's not a single particle, it's a wave, it's a property that extends over time. Now we do another experiment. We do a quantum experiment, and we put a single photon. So we dim the wave of light to very few particles, one at each time. So it's still a particle, single photon, one at each time. But the thing that happens is that the photon, when it does interact with the slit, and it expands as a wave. But since there is nothing on the other side, it will be collected in one spot only. Because it's one photon. You don't have the full statistic. Suppose then you send another photon through the slit, it will do the same thing and it will be collected in another point. And then you send another photon and so on. And there will be a statistic of these photons that will be slowly appearing like a full statistic that we saw before for the wave as well as for the bullet. So as you can see, this is already an intermediate experiment because we are reconstructing point by point a Gaussian with a wave. And this is a purely quantum mechanical effect because it does propagate like a wave, but it collapses like a particle in a single point, and it's created as a single point, as a particle. So this kind of show the collapse and the kind of wave-particle duality, but it's not enough, because how do we know that the photon is actually um, acting as a wave when it propagates? We understand with this experiment that is generated as a particle and it's collected as a particle. But what do we know about the wave reality of the photon? So let's see what happens with the double slit. With the double slit, we have one ball here, or well, we have many balls, classical object, and then we shoot them in direction of the aperture. As you can imagine, there will be two lumps of balls, one in front of the first aperture and the other in front of the second aperture. And then there will not be much interaction between the two, because we are sending one photon at each time. So there will be one bump and another bump. It's basically the sum of two probability, P1 plus P2, and they are both Gaussian. And this is what happens when you have classical particle. Let's see what happens when you have waves, classical waves. So we remove our particle. We have two Gaussian there, and that are gone. And then we have one wave. It must be one wave. I will tell you why. Because the phase must be the same between the two aperture. So the waves hits two slits at the same time, and it creates two waves that will propagate like on a lake, on water, for example, and will create some interference between them. Since the phase is the same, they are called coherent. We have a video on coherent waves. And then when they will hit the screen, there will be an interesting feature, because the intensity will go like this. Actually, you see that the maximum is at the center, where there is no aperture. It's in front of the wall. So how come is this possible? This is possible because these are two waves that interfere. Depending on the distance and the width of the slit, you can get different fringes with different width here, D, and different height, H, depending on the distance here and the wavelength lambda of your wave. And this is called interference. Is a purely classical. It's a classical effect. We have it in the radio. Whenever you see the screeching noise when you tune your radio, we have it in telecommunication. We have it in surface wave on the sea or on a lake, and we have it with light in this experiment. So we see interference. So there are crests, ups and down, because the two waves sums, and the probability is actually P1. A1 actually should be electric field 1 plus electric field 2 square modulus square will be modulus square 1 plus E2 plus E1 times E2 cosinus phi, where the phi depends on the slit and the wavelength of the experiment. And this cosinus is exactly this oscillator behavior. And as you can see, this can be seen as P1 plus P2 plus interference. So it's different from previously, because previously there was no interference, but now there is. We can, and this still classically explained. It's very easy to explain it classically. We can remove the interference quite easily just by blocking one slit. If we block one slit with a stone, for example, there will be only one wave. Nothing strange will happen. And as before, we will have only one bump, no interference happening again. And this is what happens with a wave. Okay, now we do the classical experiment, the quantum experiment. So we open the two slits, but we remove the wave, we dim the wave to single photon level. So we have single photons that are hitting, they are propagating as waves. They are hitting the slits, one at each time, but since it's a wave, there will be 2-point source where the photon will propagate. And in this sense, you have a superposition of two of the same photon in 2 points, psi1, psi2. They behave like a single wave, psi1 plus psi2, but they propagate like a wave. And how do we know that? Because when we detect the photon, it will happen in only one spot at a time. But then we will detect in another spot at a time. And another, again, each photon will have its own. As you can see, you don't have the full interference at the same time, but gradually will appear a shape which resemble very much the interference pattern that we saw before, just made with one photon at each time. So you will collect many photons, and as you will have interference behavior, but you have to wait for it to appear. So you need to collect the statistic of each single photon, because each experiment is a single photon. This means that when the wave is propagating, the two photons are interfering. They are doing something. They are summing each other. And when there is the collapse of the wave function, very much like the modulus square of the power in the electric magnetic field, you will have psi1 square plus psi2 square plus the cosinus of phi, which is this oscillatory term, psi1, psi2, which is basically depending on the slit and the wavelength of the photon. Okay, so it's, as you can see, it's a mixture of wave and particle, because we can see the wavy appearing due to the coherence of the wave and the interference, but we see that it's a particle behavior because it happens one photon at each time. Okay, so of course we can say, but wait, aren't there two photons? Does this mean that we have two photon at each time? No, it doesn't, because we can again do the experiment. We can measure every time a photon happens here. We will see what happens, and then we let one slit open only, the other measure, and then we post-select only on those events that happens with one slit open. And then we will see that with time the interference will be gone. There will be no interference because the wave 2 is gone, the wave 2 is gone, and there will be only psi1 square, which is a Gaussian again. Okay, so summarizing what we said, we talked about a classical single slit experiment where we saw the distribution of a Gaussian appearing in every case, single photon as well. The only difference is that the single photon happens one point at each time, not like the balls, like the classical balls, not like the wave that happens at the same time. And then we said that then the quantum object does have some particle and wave behavior, but the wave behavior was a bit hidden in the first experiment. So we had to use two slit to show that there is interference between the single photon and itself, actually. And this interference is coming out because of the wave particle, of the wave properties of the wave function, psi1, psi2. And this is exactly this cosinus phi, psi1, psi2. And phi will depend on lambda and the slit, and the double slit, and the distance of the slits. And this interference is what makes us tell that quantum reality is richer, because there is some hidden world where the wave function are interfering, and then there is the collapse of the wave function that tells us what happens in reality with the probability distribution. Okay, so I will give you here just a highlight of the two distribution, one, and then there is the other one where we have two bumps, or we have the intensity distribution of the single wave, and then we have this intensity distribution given by single photons, one at each time, that builds up the same shape as the wave, but one photon at each time. So having said that, we can see this kind of wave particle duality, which is a very important concept in quantum mechanics. It's a weird one, but very interesting. Okay, I hope you like. Follow me for more, and I will upload also the video with some animation to do a bit of maths on this experiment. See you next time. Bye.